Let's move now, if we may, to Professor Richard Horne. As I mentioned, Richard is head of space weather at the British Antarctic Survey, and those of you who live in Cambridge will know it well. Those of you who are in Russia may be less familiar with it, but it's an extremely distinguished research outfit, researching, needless to say, what goes on in Antarctic. Richard has a very distinguished record of researching space weather, has won many awards, and is now going to talk to us about it. Richard, please, if you would.
Okay, thank you. Great. Okay, thank you very much, Mike, for the introduction, and thank you very much also, John Cook, for inviting me to come along and give this talk, and very much also to Valerie for things technical making this happen. So I hope you can see on the screen there, what you see here on the left is the sun, and what you see on the right is the Earth and the Earth's magnetic field extending out into space and has an outer boundary. And we're going to talk about space weather. All space weather really begins with the sun, but the effects are felt at the Earth. And so in this talk, actually, I'm going to start with the Earth. I'll give you an outline of what we're going to cover. Just a general overview, all the systems which can be affected by space weather. And then we'll go into some of the science about coronal mass ejections coming from the sun and how they might affect power grids, satellites, GPS communications. Radiation storms, another area, and their effects on aviation, satellites. We'll touch on some economic uncertainty around space weather and talk about some of the challenges that we face and we're trying to overcome. So that's the outline. So here is the general sort of picture of some of the systems which can be affected at the Earth. So as I say, everything starts with the sun, but the impacts really on a variety of different systems. Satellites, and damage to satellites, particularly from high energy charged particles, electrons and protons, damage the electronic components, causing disruption, in some cases total loss. Disruption to the signals that satellites broadcast, that may be GPS signals, maybe mobile phone signals, can be interrupted. High energy charged particles can cause additional radiation dose to aviation, aircrew, avionics, and communications blackouts at high latitudes on polar routes. Some of the really important things really for you and I and everybody and the government is somewhat concerned about was the possible effects on the power grids. Currents are set up in the power grids, which actually have in the past caused blackouts to the power grids. In Quebec is a famous example. And they can set up currents in long pipelines as well, disrupting the protection systems, and they can disrupt communications with different systems, including those to submarines. So there's a whole range. It's a very multidisciplinary type subject involved in here, and we'll try and go through different areas, some of the most important areas. So I'm going to start then with the sun, and we're going to talk about coronal mass ejections. So in this little video here, this is actually from 2003. The sun is actually behind this disk here in this sort of circle, and it's blocked out so that you can see the corona, and you can see the material which is flowing off of the sun, the solar wind. So these are high energy charged particles which come out of the sun, and they take with it the solar magnetic field. And in a minute or so, you will see a real space weather effect. So this is taken by the SOHO spacecraft. It's a coronagraph on the white light. And in a moment, you'll see speckling on the detector, which is a space weather effect. There we go. I'll freeze it there. So these are highly charged particles which have been accelerated at the sun, and they've come towards the Earth to the spacecraft, and they've gone into the detector, and they're causing disruption to the electronic components in the detector itself. It's a lovely example of a space weather effect. So if you're trying to use a star tracker, something like this, it goes blind for a little while. So these coronal mass ejections are billions of tons of charged particles emitted from the sun, and sometimes they come towards the Earth. Let's stop this one and go to this one. So this video here is actually an artist's impression, if you like, a video of what happens. So here's a coronal mass ejection. In this case, it's coming towards the Earth. It draws with it the solar magnetic field. It sees the Earth's magnetic field as an obstacle, flows around it, could rip open the Earth's magnetic field on the day side, load up magnetic energy in the tail, and then particles accelerated along the field line and create the aurora at high latitudes. Let's run that again. So a coronal mass ejection, in this case coming towards the Earth, it draws with it the solar magnetic field. And I'm going to try and stop it here. So magnetic field is basically a plasma, which is a collection of electrons, protons, charged, which draw with it the solar magnetic field. But plasmas are strange things. They don't like to mix, or special circumstances where they do mix. When the interplanetary magnetic field has a component which is oppositely directed to the Earth's magnetic field, then we can have this process whereby the field is ripped open and energy is loaded into the Earth's magnetic field. You can see the field is drawn over the polar cap, and then energy, or the field, is actually, the flux, magnetic flux, is increased in this region over here, the tail region. That field builds up and up and up, and you can see now that the Earth's magnetic field is distorted. And the magnetic field lines are directed into the planet in the northern hemisphere. They come out of the planet in the southern hemisphere. And so if you remember back to your basic electromagnetism, there's a current which flows, and these across and out of the plane of the board, or plane of the screen here, to be consistent with the current, with the configuration of the Earth's magnetic field. So the energy is being stored, and then it's violent release, quickly released like that. The field snaps back. This is what we believe happens. And then charged particles accelerated along the field line, and they strike the atmosphere and create the aurora. This process can repeat, and can repeat for hours. And we have a very large magnetic storm. And the storms can take a few days to recover. And that's when we start to get some really severe effects. Okay, and so I thought I'd put this, this video in. This is the Antarctic. This is our research base at Halley in the Antarctic. And you can see this is speeded up. You can see by the stars moving across. You can see the aurora above Halley in this case. It's very beautiful. If anybody has actually seen it for real, you can go up to northern Scandinavia and see it quite frequently. It's a very beautiful effect, but actually it has some real consequences for us. Because this is what we see as a physicist, this is what we think of when we see that beautiful aurora taking place. What's actually happening is we have a series of electrical currents which are flowing along the Earth's magnetic field, into the upper atmosphere, through the upper atmosphere. In this case, you can see Peterson currents here flowing across the polar cap, out into space again, and you can see that there are other current systems which come in and join. So it's a complicated current system. And these systems close on the outer boundary of the Earth's magnetic field on one side, through the polar cap, and close on the outer boundary of the magnetic field on the other side of the Earth. Now, these currents flow at something like 90, 120 kilometers above our heads, and they're millions of amps. Millions of amps, so they're very, very large, and they're not steady. You saw the aurora. It's not steady, it's changing all the time. And that's where the impact on the power grid starts to come in. So, okay. So if I can show this slide here, we'll talk about a geomagnetically induced current. So up here we have the aurora, and the aurora, as I said, has currents, and those currents are not steady. So, and of course, electrical current which flows generates a magnetic field. So we have a changing current, and we have a changing magnetic field, a dB by dt. So that sets up an induced electric field in the Earth's crust, shown down here in green. Okay, It sets up a geomagnetically induced current down here in the Earth's crust. But of course, the Earth's crust is actually rock and it's fairly resistive. So some of that current will flow, if it can find a pathway, up through the transformer and into the power grid and along the power grid and then back down through another transformer and on and complete the circuit. And so this is a dangerous, or not a dangerous, but you know, it's a very undesirable effect for the power grids. It can affect the high voltage power grid. It can affect railway lines and signaling systems, and it can affect oil and gas pipelines, these very long conductors. These induced currents put an additional load on the system, and unless the system is protected very well, we can actually get power blackouts as a result of this. So 1859 is the Carrington storm. It was the largest geomagnetic storm we know of, and it disrupted 19th century technology. The telegraph system caused fires in telegraph offices because they used flammable paper. 1921, there's a large magnetic storm that disrupted the New York Railway. Easter Sunday, 1940, was the first power grid effects started taking place in this country. 1989, there was a blackout due to this effect in Canada for 9 hours. 6 million people were affected, and this is one of the transformers which was burnt out. Basically, the currents go through, and of course, you have an AC system. But what you're doing is you're actually offsetting the zero level, if you like. So the transformer starts to operate outside its design specification, and we get ohmic heating of the windings. And in this case, you can see what happened to the transformer. 2003, there was a very large magnetic storm, caused a blackout in Malmö in Sweden, damage to transformers in South Africa, both north and south are affected. So the question is, and one of the really important questions is, okay, so what is a realistic worst case? How much can the power grid be affected? And this is one of the reasons why the UK government got really took this on board and decided that this is an important risk which needs to be assessed, and in collaboration with the US, and signed agreements to actually try and work on this aspect of space weather, and in fact, all aspects of space weather. So there's a publication from Thompson et al. In 2011, where they were estimating the largest rate of change in magnetic field, that's the thing you can measure on the ground with magnetic magnetometers, was around 1 to 6,000 nanotesla per minute over a 1 to 2 minute time period. That would be enough to give voltage instability and regional outages. And in a report for the Royal Academy of Engineering, published by Paul Cannon and many other colleagues, myself included, estimated that something like 6 transformers would be damaged in England and Wales and another 6 in Scotland. Scotland lies further north, of course, and it's much closer to the Aurora region where these currents flow during large magnetic storms. So there's a lot more work to be done on the power grids to actually assess the risk, which would take into account the, sort of the layout of the grid, north, south, east, and west. It's very important. So that's one area, and it's a very important area which space weather affects. Let's move on. Let's move on and cover a whole range of topics. Let's look at the effects on satellites. This is another video, and it's showing here the Earth's magnetic field, and color-coded are the Earth's radiation belts. These are high energy charged particles trapped inside the Earth's magnetic field, and they circulate all the way around the Earth. It takes about 10 minutes to go around. Millions of electron volts in energy. And you can see that they're dynamic. This is actually color coding. It's actually real data. I'm sorry, I haven't got the color coding here. It's actually real data taken from spacecraft as it's being put onto this map. And you can see there are actually 3 belts. There's an inner belt and a storage ring and an outer belt, as we call it. On this scale, the space station flies underneath the inner belt. You do not want to go through the radiation belt. You do not want astronauts exposed to this kind of radiation. Geostationary orbit, where most of the commercial satellites fly, is out here on the outer edge in a region which is very variable. And the GPS type satellites fly right the way through the heart of this radiation. So, okay, let's reset, okay, recycling. So all those satellites have to be designed to withstand the radiation in space. And there are very good design programs to actually do this. Well, what's difficult is the variability, capturing the variability and understanding what is a reasonable worst case, and to try and assess how many satellites might be affected. So the radiation damage to satellites occurs in a number of different ways. So the first I'll mention are single event upsets. This is where something like a cosmic ray, a very high energy charged particle, just goes right the way through the component, and it can change the state of the memory. So change a 1 to a 0, something like that. There are other different types of upsets which can occur as well. They're called single event upsets. Mostly they can be reset from the ground, or intelligent software on board can actually deal with this, providing it's not overwhelmed, providing the flux is not too high. And when we have a radiation storm, sometimes it can be very, very high flux, and this may get actually overwhelmed. Another area is surface charging. The satellite flies in a plasma, charged particles, and some of the satellite is in sunlight, so you have a photoelectric effect, Einstein's photoelectric effect, and the other surfaces are not in sunlight. And so you can get differential charging between the different surfaces on the spacecraft. And if that becomes severe, you can get an electrostatic discharge, which can destroy some of the components. A third, and perhaps one of the most important, is internal charging, or deep dielectric charging. This is mostly due to electrons which penetrate the outer skin of a spacecraft and then get buried in the insulators internally in the spacecraft. So charge builds up and up and up on the insulators. And if the radiation levels go high and remain high, that charge can build up and can break down the component and actually permanently damage it. Several spacecraft have been lost due to this kind of process. These charged particles are so energetic, it's very difficult to shield against all of them. One of the mitigation strategies is to put shielding around the sensitive electronic components, which takes out most of them, but still some of the charged particles can get through. And it's a delicate balance between how much shielding you put around the component as to what that's going to cost in terms of launch costs and operational costs. Another area is degradation of the solar arrays from all kinds of radiation, particularly radiation from the sun, solar protons. And they gradually degrade the power that you can generate from the solar arrays over a period of time. So designers have to be very careful how they size the solar arrays. So how bad can it be? This is an example from 2003 of a large magnetic storm. It's known as the Halloween storm. It took place between 23rd of October, 6th of November. And so what I'm showing here is distance away from the Earth, measured in Earth radii. Geostationary orbit is at this level, on this red line going horizontal. And you can see the time scale, so October, November, December, going along the bottom. And color-coded is the electron flux. This is greater than 2 MeV electrons, so high energy electrons. And you can get an impression of how the radiation flux, how the number of high energy charged particles varies, almost disappears, comes back, intensifies. This is when the storm hits in here. The radiation belt, which is normally at this kind of location, was depleted and then reformed much closer to the Earth in this region here. And then that was depleted and then reformed back at its usual location over here, quite intense, and you can see the variability as it goes on. This is the outer radiation belt. The inner belt is down here, and you can see there's a gap between the inner belt and the outer belt. It's called the slot region. And some satellite operators have now started launching satellites into this slot region in the belief that actually the radiation exposure in this region is a lot less. And most of the time it is, except when large storms like this come along, and you can see those spacecraft will be subject to a very large dose of radiation. So you better make sure you design them right. During the storm, one satellite was total loss. It was $640 million. 10 satellites lost service for more than one day. 47 reported anomalies, that is, malfunctions. 10% of the entire fleet were affected during that period. And at that time, there was about 450, 500 satellites operating. That was back in 2003. What would happen today? What would happen today if we had a very large magnetic storm occur again? And this storm was by no means as big as the Carrington storm of 1859. Let me put that in context. This is a satellite population over the last 2 solar cycles. So in black here, you can see the solar cycle. This is a sunspot number, daily sunspot number. And then you can see we didn't have such a large sunspot maximum over the last cycle. And we're in here somewhere. The number of satellites being launched and operated in geostationary orbit is steadily increasing. Okay, so you've got around 500 or so at the moment, just over. But look at these satellites in low Earth orbit. You can see as well as I can how much this has increased just recently. And it's just going way off scale, over 2,000. These are the spacecraft like the Starlink constellation, OneWeb, and there are thousands of satellites due for launch over the next few years. So we're increasing this population hugely. And the other point I want to make here is this population of spacecraft have never experienced some of the space weather we've had during solar maximum periods. So again, we want to make sure that they ideally have designed them right so they can weather the storm. Let me move on and talk about another aspect of space weather during a magnetic storm. Disruption to global navigation and satellite systems. GPS, of course, is the one that perhaps we're most familiar with, operating between 1.1 and 1.6 gigahertz. But we also have the European version of Galileo signals, and there, of course, there are other Chinese and Russian systems, an equivalent, and an Indian system too. Magnetic storms perturb the upper atmosphere, they disturb the ionosphere. Electric fields are created which actually can enhance the ionosphere. And this is particularly so in the equatorial region, you can see here. So you can see the United States in the north and South America in the south down here. And you can see in red, these are changes, perturbations, it's measured in tech units. For that, read increases in or changes in the ionization, the amount of ionization electrons, if you like, on the path between a satellite, a GPS satellite, and a receiver on the ground. And you can see that actually there are changes and it's irregular, and this can be quite dynamic during a storm. These changes in the ionosphere cause an additional delay to the signal, and that can be corrected by a model. But the model can't always deal with the fact that there can be very large gradients in the ionosphere, and it can't always pick those up. Another really important aspect is scintillations. That is, you can have irregularities in the ionosphere which scatter the signal, and they cause amplitude and phase variations in the signal, so much so that you can lose the phase lock and you lose the signal over a period of time. Well, you've got the signal, but you lose the phase lock. A reasonable worst case, we came up with an assessment a few years ago. Errors in a reasonable worst case can be up to 100 meters in the location. And perhaps just as important, perhaps maybe more important, the signal can become intermittent. So, sometimes you got the signal, sometimes you haven't. Sometimes you got the signal, sometimes you haven't. It's a very difficult thing if you cannot rely, if you're operating a service and you cannot actually rely on during a severe storm. It's really important. So This is shown mostly in the equatorial. You get the equivalent, actually it's not really so apparent actually on this diagram, in the aurora regions at higher latitudes where we have the aurora, and down in the south too. Let me move on to another aspect, satellite drag and orbit decay. So the magnetic storms we've been talking about, they can set up the aurora, they set up electrical currents, and those currents will heat the atmosphere, and the atmosphere expands upwards. So this is just to set the scene. This figure over here, you can see the Grace satellite up here in blue, and you can see it operating around about 500 kilometers, maybe just below, and then gradually starting the orbit starting to decay. And then here's the Champ satellite operating at lower altitude, orbits decaying, gets boosted up, decays, and then re-enters, come down here. In 2005, there was a storm, and there's a very interesting set of observations. This is measurements of the interplanetary magnetic field. As I was saying here, the magnetic field turns southward, opposite direction. Negative means opposite direction to the Earth's magnetic field, but it only does so for maybe a few hours or so. Turns northward, and it's fluctuating. The satellites measured an increase in the density at Champ around about 350, 400 kilometers altitude. An increase in the density because of those currents had heated the atmosphere and it expanded upwards. And so that spacecraft, its orbit decayed by about 80, 100 meters over that period, over a period of what, 2 days. Now, it's not obvious what happened when you actually look here at this time. And you might think, well, 100 meters drop, but is that really important? It is important when you think of it in terms of space debris. So let me go back to another storm, a very large storm in 1989, and where we had the Americans actually track spacecraft, and they track space debris. The yellow line indicates a measure of the intensity of the storm. It's the AP index. And after that storm hit, there were thousands of pieces of debris and satellites, which, as they stay there on that slide, were not where they should be following that storm. In other words, they lost track of thousands of pieces of space debris. The US system actually tracks everything above 10 centimeters and is developing a system to track smaller pieces of space debris to try and warn of collision between satellites and space debris. It took days to reacquire all these pieces. Today, it's estimated 130 odd million pieces of space debris that could disable a spacecraft, all in different orbits. According to the European Space Agency, there was something like 580 collision alerts last year in 2020. That's a huge number. And this is the growth in space debris. You can see the effects of, there was an anti-satellite test, Chinese anti-satellite test, increased the number of space debris tremendously. There was a collision between two spacecraft, increased it here, and this plot actually, okay, and it goes up to about 2012. There's an increase from there. So this is a significant, really important issue. And as I say, we're putting up thousands of new spacecraft up into space. So collision avoidance and warning systems are really, really important. Space weather affects us because it changes the atmosphere and it can change the orbits of spacecraft. And typically we're looking at 500 kilometers and below. That's the regions most affected, though we don't really know how far up it extends. The effects may take place. Let me move on to another aspect, solar energetic particle events, radiation storms. So this is another way in which space weather affects us. So on the plot over here on the left, on the artist's impression, we have the sun. We had a coronal mass ejection, which is coming away from the sun. Here, the interplanetary magnetic field is shown. The Earth is over here. And we have a shock wave that's formed. This plasma comes off the sun and it's traveling so fast. It's traveling faster than waves can travel in this medium. So plasma, we have alphane waves, special types of waves which travel in this medium. So if you're traveling like that, the usual conditions, you get a shock wave. And a shock wave can be a very effective way of accelerating charged particles, protons in particular, to very high energies. So we get a shock front, which causes acceleration of the protons, and then they largely follow the magnetic field lines and impact the Earth. So again, I'm just reminding you, this is an example. We've seen an example of this before, protons. Okay, this is flare related, a CME related. And you'll see the detector, or the impact of the protons on the detector. This is from the year 2000, July is 14th, it's a Bastille Day. It's known as a Bastille Day storm. This is the measurements from a spacecraft, polar orbiting spacecraft, going over North Pole. You can see the UK over here, Scandinavia. You can see Canada over here, and Russia. And as the spacecraft goes over, you can see the detectors detect high energy protons as they go across the polar cap and then down again. So these particles is evidence that these particles can penetrate the Earth's magnetic field, mostly in the polar regions, because the orientation of the field, and the field is a bit weaker in space, and they can get down into the atmosphere. Actually, they energetic enough above about 500 MeV, they can get down to the ground. At lower latitudes, the Earth's magnetic field gives us protection from these particles, and of course the atmosphere too. So that the polar regions are really, really important in this region, and gives you one of the reasons why, working the British Antarctic Survey, we get involved in space weather. As these particles come down, they strike the upper atmosphere, they increase ionization, and the ionization absorbs radio waves in the D region. It absorbs high frequency radio waves, 3 to 30 megahertz. And that's important because it can cause a radio blackout, particularly for aircraft and aviation. So here's some data for that event, the Bastille Day storm. And I just want to show you this here. This is the number of particles as a function of time, 3 days. Look how quickly that event took place. Look how the rise time of that. It's incredibly quick. And then the proton counts lasted for a few days and took several days to recover. So we might get 1 to 3 of these per solar cycle. In 1959, we had one of these events. It lasted for about 15 days. The radio blackout lasted for about 15 days or so, because there was more than one event. And we know what we're trying to do. One of the things people are trying to do research on is to say, well, what's the kind of biggest event that we could have, and what would be the impact? And one of the things that we know is that the radiation creates different kinds of isotopes, which can be precipitated out and then become trapped in tree rings and ice cores. And recent work is shown by a paper by Hare et al. Looking at beryllium-10 and chlorine-36 in ice cores, that in 660 BC, there was an event 10 times bigger than anything we have ever recorded directly, in modern times. So the largest event in modern times is 1956, and it's bigger than the one I'm showing here. But there may be something 10 times higher than that if we look back in history. And they affect aviation. So aircraft still on very high latitude routes use HF for communications. They have to do that. And in one of these events, you can lose radio communications, 330 megahertz. It's important for aviation. It can also cause upsets and failures in the avionics and aircraft, and additional radiation dose to aircrew and passengers. And that's something which is very important. It has to be monitored by law and assessed by law. A recent paper estimated that in 1956, if we'd been flying London Heathrow to Los Angeles, you would have got a 7 millisievert dose on that high latitude route. And for a 1 in 100 year event, that's kind of like the standard which is used is, what is a realistic worst case? Well, look at a 1 in 100 year event. Estimate is something like 28 millisieverts on that route, where the annual limit is something like 20 millisieverts. So you'll be over the annual dose on one flight. So it's really important. Actually, aircraft operators re-roster people if they get anywhere near 2 millisieverts on a flight, so as to protect their aircrew. So this is an important aspect. Just say a few words about economic uncertainty. The original estimates of the impact of a extreme space weather event were estimated around $2 trillion, and that may be about 10 years ago. And for satellites, that was mostly based on the power grids. For satellites, it was estimated the impact could be as high as $30 billion. Now you have to take into account the cost of the spacecraft, the cost of launch, cost of replacing them, and the reduction in their lifetimes. Space weather was put on the National Risk Register in 2011. There was collaboration between the US and the UK in particular. Agreements were signed by President Obama and Prime Minister Cameron. It's been updated a number of times since, most recently last year in 2020, where space weather is still regarded as a very important risk. Not as high as a pandemic, of course, but still important. More recent economic estimates, between something like $7 to $42 billion per day lost to the US economy. This is US only, due to a power outage. And the way the economists work this out is, if you lose power, the power grid, your ability to produce goods is is impaired, and so you can work out what the economic loss would be for due to the gross domestic product, and then you can factor in the supply chain as well. So that's basically how they go about doing it. And of course, this number varies according to the severity of the storm and prediction measures. It's a very difficult calculation to do. There's a lot of uncertainty in it. More recently, for a 1 in 100-year event for the UK alone, it was estimated that based on our current forecasting capability, the impact could be as high as something like £2.93 billion pounds. But if we actually invest in small forecasting, replacement of satellites, for example, as aging and more capability, that could be, the impact could be reduced down to something like £1 billion. And that's where it sits on the National Risk Register if you go and have a look. So the government actually has invested, the UK government is investing in space weather. We have a forecasting system run by the UK Met Office, and there is a large program called SWIMMER, which is 20 million research program, which I'm helped put together, and which we're a part of now, very looking at both the forecasting and the 1 in 100-year type events for space weather to assess the impact. Challenges. I want to just talk about some of the challenges in sort of last two slides or so. And I want to just highlight really the timescales and the difficulty of trying to do a forecast. So as we all know, light, X-rays take something like 8 minutes to reach the Earth, sun to Earth. So you've got 8 minutes, and okay, if you had a solar flare, you see it 8 minutes later. The radiation storm I've just been talking about, actually, you have the 8 minutes plus a few minutes. These particles are so energetic, they can arrive just a few minutes after light comes along. So they're highly relativistic. So it doesn't give you a whole load of warning. A coronal mass ejection, as we've been talking about, these tons of charged particles which are coming out, the quickest that we know of, evidence for, sun to Earth is 14 hours. 14 hours, 40 minutes, if I remember correctly. Usually it's 1 to 2 days, but it can be as quick as 14 hours. Most sort of systems like the power grid and satellites say they want 24 hours warning, thanks very much. It's very difficult to do. And once a coronal mass ejection gets to the Earth and it can trigger a magnetic storm, that storm can last several days. So that gives you an idea of the timescales. Where we are, this is my assessment of where we are in space weather forecasting. We cannot predict a coronal mass ejection reliably. We can't predict when one's going to take off reliably. We can't predict when a radiation storm is going to take place. We can't do that reliably. We can look for precursors on the sun. We can look for large sunspot groups. We can look at active regions. We can look at other features. And this is what the UK Met Office does 24 hours a day. And we can get some warnings. We see a large sunspot group or something becomes very active and we see it starting to track across the surface of the sun. It gives us a sort of level of warnings, and we should start to be prepared. We can measure the interplanetary field at the L1 position. That's the position between the sun and the Earth where the gravitational fields balance. And you can put spacecraft there to do the monitoring. As I said, the direction of the interplanetary magnetic field is absolutely key to measure that. But the trouble is, once we measure it with a spacecraft at the L1, it'll only give us 30 minutes reliable warning of a severe magnetic storm. And these are the sort of challenges that we are faced with. This is something, okay, that we're doing at the British Antarctic Survey. This is my team. We're trying to do a risk prediction and radiation forecast system. And okay, I'm not going to go into details of this, but what we're trying to do is we do a model which we actually reconstruct the radiation belts for the last 7 days, and then we do a forecast of the next 24 hours of what the radiation level is going to be. And then we compare that with what was actually measured by one of the spacecraft. So our forecast there is in red, and what the spacecraft actually measured is in black. So it's one of the things we've done, and we've actually, we've taken the software and we've licensed it to the UK Met Office. They now have access to this, and we're developing it with them in collaboration with them to put this in. We're also doing a project with the European Space Agency where this is due to be released later this year. So in summary then, I'll draw to a close. Our modern technology has become vulnerable to space weather. We've grown dependencies which perhaps we weren't really aware of when we were developing our systems. Our power supplies have become vulnerable. Satellites, the miniaturization of components has made them more susceptible to charged particles. On the other hand, you know, we have better design too. So it swings and roundabouts in many ways. Communications, navigation, aviation are susceptible to space weather. In the research area, we need to understand better what a 1 in 100-year event looks like. We need to analyze data, various different types of data, even tree rings and ice cores as well, as sort of like our modern day data, to try and assess how big a 1 in 100-year event will be. We need to try and model it and try and understand it and put it together, the various different aspects of the system. And we need to improve our forecasting capability. And when we do all that, we need to then assess what the environment is. And then we need to talk to people in companies and look at the impact, then better able to assess what the impact on their system is, and then actually feed that back into mitigation strategies to protect them, design away as much as we can the risk. So I'll stop there. Thank you very much for listening. Thank you.
Well, Richard, thank you very much indeed. That was totally fascinating. I suspect everybody like me was absolutely rapt at the range of things of which I at least was completely unaware, and the implications of all that for our everyday life. So thank you so much. Well, if you're up for it, may I throw a few questions at you as sent in by our viewers. George P asks, what is temporal intensity correlation between solar spots and the storms?
Okay, we have sunspots which follow 11-year solar cycle, as I showed in one of the slides. And there is a similar variation in the number of magnetic storms or magnetic activity at the Earth, disruptions at the Earth. But it's not always clear. There seems to be a general lag in the magnetic storms at the Earth. The peak in the the magnetic storm cycle seems to be 1 to 2 years behind a peak in the solar cycle, in actual fact, which is a bit curious. You might get okay, so we use the sunspot number as a sort of a measure of the activity on the sun, and the material which is coming off of the sun, the coronal mass ejections, comes towards the Earth, but it does not always trigger a magnetic storm. And the key ingredient is the direction of the interplanetary magnetic field. As I was saying earlier, it's always fluctuating. When it goes southward and it stays southward for a prolonged period of time, that will trigger a magnetic storm. If it remains northward in the same direction as the Earth's magnetic field, it won't trigger a large magnetic storm. And so that is one of the key things, and it's very, very difficult to measure. So there is a general relationship. There seems to be a bit of a delay in the peak at the Earth, but it is not one-to-one.
Interesting. Can I just remind the audience, please, if you would like to ask a question, we'd be pleased to see it, but please could we ask you not to use the chat function, but to use the Q&A for your written question, or raise your hand and we'll try and bring you in on the telly. So anonymous attendee, who's rather coy but asked an interesting question. Even if you could predict an event, what could you or the infrastructure operators do about it?
Okay, yes, that's a very good question. All right, let me take the power grids. The power grids, they actually do take warnings from the UK Met Office, and they do things already. So what happens in a large magnetic storm is you put additional load on the power grid. So one of the things you would actually do is you'd actually step up generation to have more power available to deal with the load. That's one thing you would do. You might actually, there are other kind of being prepared. It's about knowing and being prepared. So for example, another thing which, like my colleagues of mine who are satellite operators who work in SES, and they operate the largest satellite fleet in the world out of Luxembourg. They said, well, okay, it's really important for us to know what's going on. We just need one spacecraft to go wrong, and it ties up an operator trying to deal with it. And we've still got another 53 satellites we need to go and operate and make sure are functioning well. So for them, it's about rostering more people to be available. If we have advance warning that there'll be a period of high risk, we would have people available to deal with it. Another thing the satellite operators said is that, well, you know as well as I do, how many times does your computer do an upgrade, a software upgrade? We would delay doing anything like that if we know it's going to be a period of high risk. We do not want to increase the risk, we want to minimize the risk. So if we have a period of increased risk, we would delay a software upgrade. We would delay an orbit maneuver. Satellites are always being sort of like maneuvered to station keeping quite frequently, or maneuvered to a different slot. So there are things like that that they can do to minimize the risk. One of the things they say is we do not want to make anything worse. That's uppermost in our mind. And we also will inform some of our customers, you know, some of the services which they may be relying on may be at risk, and that may then be things which they choose to do for their operations. They may choose to do their operations differently or delay their operations. So for satellites, you know, they're saying we will continue operating, we will continue broadcasting or doing whatever they do, but there are the sort of next layer, if you like, of activities and actions that they would take. It's very important for them. And that's true right the way through. For aviation, if they have a good warning that, or even actually if something comes along and it's in progress, what they'll try and do with the aircraft, and they have done this before, is to fly the aircraft at lower altitude, if it's possible, if they've got enough fuel to do it, to take cover, if you like, so to reduce the radiation exposure of the aircraft. And if it's a very severe one, they'll prevent aircraft from taking off. In 2000, I think it was, I can't remember now, I think it's 2005, there was an important space weather alert, and it did affect aviation significantly. So there's sort of examples of some of the things that people will do.
So I've got a question from John Cook on video. And could I ask the person who did ask their question on the chat by mistake if they would ask it on the Q&A or raise their hand, and we'll get you back in. John Cook, please.
You mentioned, oh, that was a fascinating talk, Richard. Thank you very, very much. A very worrying talk as well. You mentioned the errors with GPS, and struck me. I mean, I first looked at it, said, 100 meters, that's not very much. You can see your way around 100 meters. But if you're a self-driving car, you need a great deal of greater accuracy than that. Do you know the extent to which this proposed world of self-driving cars and electric cars is going to be influenced or vulnerable to storms like this?
Well, that's a very good question. We kind of call this emerging risks, where you have all these new developments and technology sort of going forward. Yes, it is a concern, and it's understood, and people are actually looking at this carefully. I think the important thing to realize that what I was showing is a reasonable worst case. That's a 1 in 100-year event. But it does raise concern because, if you're going to be using GPS type systems for navigating cars, ships is another one, actually. I was really surprised to learn that actually they're developing ships, which is going to have nobody on board, which is going to navigate with GPS signals, and go from, a certain country to Europe. And I think, my goodness, I mean, would you really want to be on that ship or anywhere near it? I don't know. But they've got to have backup systems. I think they have got to backup systems, or you've got to have sort of fairly reliable warnings. I think that's got to be built in. So I think, that's where we are. I think that would be my suggestion, and I think that people are looking at that quite seriously. We have to understand the main regions where the disruption to the GPS signals take place, very much near the equatorial regions I was showing in that plot. For very good physical reasons, and also near the auroral regions as well. Now, if you have a very large magnetic storm, the aurora will start to expand equatorward. So you'll see it in Scotland, and if it's a very large storm, you'll see it down. You'll see it in Cambridge and other places too. So it is variable, but that won't happen very often. But I think you're right, actually. There is a risk for driverless cars and ships as well.
Thank you very much.
Great, thank you. Tim Gosling would like to be on the telly. Tim, would you like to ask your question? Unmuting first, as I'm sure you will.
I hope you're getting me now. You should be.
Yep, that's fine.
Does this imply that perhaps the national grid is not a good idea, that we ought to start breaking it up into smaller units?
I wouldn't want to go without electricity myself, quite frankly. I think the national grid take this very, very seriously. I know the guys who actually run the national grid, and they're very much aware of what can happen to the grid, and they've done a lot of risk assessments. So they're putting in place a lot of mitigation as best they can. One of the ways is about developing the better protection systems in the transformers to help protect it. One of the things that it's interesting in discussion that they've said is, sometimes what seems like an obvious thing to do is not the right thing to do. So there was a discussion about, well, okay, maybe you could sort of break it up or into different sort of regions or areas. But actually they're saying, well, that you have to be really careful in doing that. You don't put more load on another part of the grid, and that create something which is more dangerous elsewhere. So I don't know all about the mitigation aspects that they're actually taking, putting in place, but I do know they're very much aware of it. Upgrading the transformers is very much an important one, and actually having a much greater supply of backup transformers should something go wrong, so that they can immediately replace transformers, is also part of their mitigation strategy. But basically, they have a very difficult time sometimes, because The difficulty for them is that you might have something on its way from Sun to Earth. And as I said, we just don't know whether that's going to be a major magnetic storm or not, because we cannot measure the interplanetary magnetic field in its direction until it gets to a certain spacecraft at the L1 position, and that gives us 30 minutes warning. So they have to take a decision. Do we actually take a lot of preventative action in advance? And if we do so, that risks a lot of false alarms. Or do we decide that's not going to be such a high risk and risk missing out and having a severe event taking place? They have a very difficult job, which is why they take it very seriously. But for most of the time, they deal with additional loading caused by space weather, and they continue generating electricity.
Yes, I just wondered whether the reason for the national grid is that power is generated, generally speaking, in one place and used in somewhere entirely different. And the idea of the national grid is to distribute it from one place to the other. It seems to be a case for trying to invest in rather more localized power generation. I don't know whether that's going to be possible, but perhaps they should be thinking about something like that.
I think it's a very interesting, a very good suggestion, and I think perhaps more and more as we generate electricity from solar cells on our houses and so on like that, who knows, that might make things a little easier. But yeah, that's a good suggestion. I don't know to that level of detail, quite frankly.
Thank you.
I have another question. Thank you, Richard. I have another question from anonymous attendee. I don't know if that's the same anonymous attendee or another one. He or she says, marvelous presentation, 3 exclamation marks, and I'm sure we'll all echo that. Are the impacts to electrical design standards being considered in IEEE or elsewhere?
Electrical design standards. I'm not sure I know the answer to that one. In what regard? I'm not quite sure. I'm not sure I can answer that one quite. See, that's a flaw of me. That one. That's a really good question.
Yes, I think I'm sort of vaguely aware that what used to be called the Institute of Electrical Engineers make most of their money by selling standards for electrical circuits and the wiring regulations and so on. But I don't know about the IEEE, although the logic of the question is clear. Thank you. Can I bring in audio questions, please, from Martin Williams?
Good. Right, I've just been trying to get my camera going, but for some reason it's not working, so you've been spared that. 2 questions and very different areas. One is satellites, and to what extent is more miniaturization in terms of circuits making satellites more vulnerable? I believe that there's a tendency to use older chips because the components are that much larger and less vulnerable, and what more can or should be done to protect satellites from these events. My second question is in terms of power supply, and sort of follows on from one of the early questions, which was about should we be breaking up the grid or using it less? And of course, what is happening is there's more in Germany than here, for instance, where most homes seem to have solar panels, and of course the power is produced locally. How vulnerable are those to solar events, and could sort of separation from one area to another? I'm not phrasing that very well, but I mean, can things be divided to protect, shall we say? Yeah, 2 questions there.
Okay, and okay, so go to the satellite one first. The satellite industry, as I understand, is very conservative until recently has been very conservative in its design. Okay, so they will use tried and tested, and the insurance guys will tell you that, and use tried and tested. But it has developed so that actually miniaturization has come along, and they're using smaller and smaller components. such that they become more and more susceptible. You know, a single proton can actually fly through one of those things and change the logic state. And if you get a radiation storm, a solar angelic particle event, that can really be a very challenging environment to actually maintain the safe operation of those circuits. So it's about the miniaturization and its susceptibility to ionization by high energy charged particles. Now, you can mitigate that to a certain extent. So, for example, for the single event upsets, what they do have multiple circuits, duplicate circuits, and they do sort of majority voting, intelligent software to try and deal with it. And that works. It works a lot of the time, unless the system gets overwhelmed with a big radiation storm. And the question is, how big a radiation storm can it cope with? And that then you go into the design of all the different spacecraft, because the designs are commercial in confidence, and they are, it's not easy to get the information. As to some of the protection, you know, putting more shielding around the electronic components is something which has been done, but what designers tend to be doing nowadays, as I understand, is they're saying, well, okay, we used to calculate the radiation dose for the lifetime of the spacecraft, and not many spacecraft die because they've reached their radiation dose. So we've probably got the calculations wrong, you know, there's a structure of the spacecraft and so on. So they're trying to say, well, we shave away some of the margins. Combined with the fact we haven't had a very challenging radiation environment over the last solar cycle. And the concern for some people is saying, you know, we're just saying, watch out, because the space radiation environment has been much, much higher. And you need to be aware, and you need to actually be aware that of what kind of risk you're actually taking. And you cannot, you know, you can put lots and lots of shielding around certain electronic components, but some of the charged particles are coming along, they're just so energetic, it's just not reasonable to shield them from all of those very high energy particles. So it's a mix. It's a mix of things about, you know, designers trying to improve the design and be more effective and more efficient with the design, and knowledge of the radiation environment, you know. So that's why it's so important to try and work out what a 1 in 100-year event is, and put that into the design models. There are orbits now where spacecraft are going up into, where we have design models on the radiation environment, and the design models use data, very sparse data, which has maybe been collected 10, 20 years ago, where not in regions which have not been visited by spacecraft very often, scientific spacecraft. And so there's a lot of uncertainty. So there's a bit of a drive to try and reduce that uncertainty. So for example, OneWeb is actually going up to 1,200 kilometers altitude. So that's low Earth orbit, but it's higher than traditional low Earth orbit. Most of the low Earth orbits are below 1,000 kilometers. So you go up to 1,200, and okay, you've got the proton radiation belt, particularly in the South Atlantic, which penetrates closer to the Earth in that region, where the radiation exposure is going to be much higher. And if you go to the design model, and I've done this myself, you can actually get numbers out from the design model for the radiation environment there. But you ask, well, where did those numbers come from in the first place? It came from an old spacecraft many years ago during one part of the solar cycle. And, you know, what is your confidence in that data? We need more data to actually improve our confidence and improve that design. So there's a mix of things on the spacecraft side. On the power generation, yes, I think you ask a really interesting question. I'm not sure I've actually quite got the answer. I would have thought, you know, the more distributed the power systems can be, I would have thought that would be an advantage, but I can't put my hand on the heart and say that's true. I think you need to actually ask that of something of the people who run the power grid. In actual fact, you prompted me, because I think I will go and ask the guys who run the power grid to try and get an answer to that.
Excellent.
Well, perhaps we can correspond on that. Thank you. Thank you very much indeed for those answers.
Okay.
Very, very revealing.
Thanks, Martin. Thanks, Richard. A question from Graham Cox. Would the disruption to GPS, GNSS affect the accuracy improvement available using differential GPS? I'm not sure I understand that, but you might, Richard.
Okay, differential GPS is using two frequencies, as I understand it. And the answer is that the two frequency system is more robust. It is more robust. But the scintillations are still the problem. I think that's the main problem for the differential GPS system. And they can still be really important. I think the real answer, and the thing that people are starting to look for the GPS, if you go to much higher frequencies, then you can get away from the scintillation problem. So you're much higher. So basically, the higher in frequency you go, the less of an impact it has. So I think people are seriously looking at going up much higher. But at the moment, it still can be affected, and people have still talked about, and well, I think I put on the slide, it can be intermittent. It's believed to be intermittent, could be for a few days.
Yeah, and John's earlier question about the impact on our road transport is significant, I guess. Sandra Little, Antarctica says Antarctica has extreme regulations about what is taken away to keep a pristine environment. What about controls for satellite materials and potential space debris? Not sure it all lands in Antarctica, but it lands somewhere.
I think, well, most of the satellites, as I understand, they try and deorbit them, and they land in the sea for the things that are up there. And of course, you've got a lot of rocket stages and other bits of debris which have no, you have no control over whatsoever. Yes, there are very strict rules in the Antarctic, and let me first say the British Antarctic Survey goes out of its way to actually try and obey those rules as well, and very careful about trying to remove all waste and such like from Antarctica. I've never seen a bit of a satellite down in the Antarctic. That would be lovely if I did, or a meteorite. Actually, I'd love to go and find one of the meteorites. The Antarctic is a wonderful place to go and collect meteorites if you go to the right place. And of course, they're all protected. There's strict regulations on what you do with meteorites. You're not allowed to pick one up and put it in your pocket and take it home. But who knows? Who knows? One day.
Sounds like a great summer holiday, looking for meteorites in Antarctica. I've got a question from Phil Bowden, who says, will the expected reversal of the Earth's magnetic field affect our susceptibility to magnetic storms?
Oh, well, that's a good one. Yes, there was an interesting paper the other week actually on that, which came out in Science, and I think it was the Guardian picked up on it. Yes. Okay. So the Earth's magnetic field has gone through reversals, several reversals in history, but we don't quite know how the field reverses. Does the field actually go through zero and then grow again in the opposite direction, or does it actually become small and then rotate around? We don't fully understand how that might take place. One thing's for sure, the radiation, the trapped radiation, the radiation belts would tend to disappear or become very small. And so therefore, the shielding of the Earth's magnetic field wouldn't exist any further. So radiation storms would be a lot more severe. And so the effects that I was showing you in the polar regions, you might expect those to extend a whole range of different latitudes, mid-latitudes, equatorial regions as well, if we didn't have a magnetic field. As to what it might do to a power grid, I think that's really, really difficult to say, quite frankly, because it depends upon the current systems which are set up and which flow, and they flow along the magnetic field and through. So if there's no magnetic field whatsoever, our atmosphere would be a bit like Venus, and so the solar wind would impinge on the top of the atmosphere completely. So I think the answer in that case, if we had no magnetic field whatsoever, we wouldn't have the same kind of currents flowing, so we wouldn't have the same sort of effects on the power grid. But I wouldn't want to be around when a radiation storm came along.
Well, Richard, what a fascinating note to end on. We should let you escape. It's been an absolutely fascinating evening, an exemplary CSAR talk, a glimpse of some very deep and live science and remarkable implications of the application of that for how we understand our everyday lives. So I thank you on behalf of all our viewers. It's been a quite magical evening. Thank you so much. And I look forward to seeing you in the local pub in due course.
Thank you very much.
Thanks to you and Lachlan for a fascinating evening. Thank you both very much. Final message for our viewers. Our next speaker is, in a couple of weeks' time, is Lord Sainsbury, who's Chancellor of the University and was Science Minister for 7 years, as you know. 3 weeks' time, I should say, not 2 weeks. Thank you for John Cook for whispering in my ear to give you the right answer. Anonymous attendee, and again, I don't know if it's the same one or a different one, but the attendee says, "Thank you" in capital letters, brilliant with 4 exclamation marks, and I absolutely agree with that. Thanks again.
Thank you, Richard.
Thank you.